Here's a question. You've got a row of walls, all different heights. Pick two of them to trap water between. Which pair holds the most? The water between two walls is as wide as the gap, and only as deep as the shorter wall. We want the biggest pool. Here's our example. 9 walls of different heights, lined up like a train of numbered compartments, positions 0 through 8. The best pair is the wall of height 8 near the front, and the wall of height 7 at the very back. Watch why. The gap between them is 7 steps wide, and the shorter wall is 7 tall. 7 times 7 is 49. 49 is the answer. Notice we return one number, the size of the best pool, not which walls made it. Okay, what would you try first? The honest first idea is simple. Just check every possible pair of walls and measure each pool. Take the first wall, pair it with every wall after it. Then take the second wall and pair it with all the rest. This works. You will definitely land on 49. Every single pair gets measured, so nothing is ever missed. But count the work. With 9 walls, that is 36 pairs. Small enough. Now picture 100,000 walls instead. 100,000 walls means about 5 billion pairs to check. Your program just sits there for minutes. Measuring every pair like this is O of n squared work. Correct, but far too slow once the input gets large. Let's slow down. Only 2 things set the size of the water: the gap between the 2 walls and the shorter of those 2. Nothing else. So start as wide as you possibly can. Put 1 pointer on the first wall, 1 on the last. That's the 2-pointer move. Now the real question. We already have the widest container. To beat it, which of the 2 walls should we move inward? You might be tempted to move the taller wall, hoping for a deeper pool. Watch out, that is exactly the wrong move. Move the shorter wall. Moving inward shrinks the gap no matter what, and the shorter wall is the only thing capping the depth. Keep the short wall and the pool can never grow. Move it, and the next wall just might be taller. That is the whole trick. Let's run it. The left pointer sits on the first wall, height 1. The right pointer sits on the last wall, height 7. The gap is 8 wide, and the shorter wall is height 1. 8 times 1 is 8. Our best pool so far is 8. The left wall is the shorter one, so we move it inward. The left pointer jumps forward onto the wall of height 8. Now the gap is 7, and both walls are tall. The shorter side is 7. 7 times 7, 49. A new best. Now the right wall, height 7, is the shorter one, so we move it inward. The right pointer steps back onto a wall of height 3. The gap is 6, and the shorter wall is only 3. That makes 18. Smaller than 49, so our best stays put. From here the left wall stays tallest, so the right pointer keeps stepping inward. The gap shrinks, a few pools come close, but none ever beat 49. Then the pointers meet. Notice what we did. We never measured most of those pairs. Each move threw out a whole batch of worse containers at once. The 2 pointers only ever step toward each other, and each wall gets visited once. The time grows in step with the input. And we only kept 2 pointers and 1 best value. That memory never grows, no matter how long the input gets. Same logic, now in Python. Left starts on the first wall, right on the last, and best tracks the biggest pool we find. While the pointers haven't met, take the shorter wall, multiply by the gap, and keep that area if it beats our best. Then the key move. Whichever wall is shorter, step that pointer inward. The taller wall stays right where it is. When the pointers finally meet, the loop ends, and we hand back the largest pool we ever saw. And that's the pattern. Start wide, always move the weaker side, never look back. 2 pointers turn billions of checks into 1 clean walk.